All right, so let's go ahead and get started. So who has looked at the video from Friday? Still? Okay, it's kind of interesting. You don't find the video, but can you find the sound there? There's nothing there at all. Okay. Yeah, so here's the reason. There was a problem with the video. And the problem occurred not only with their system, but my system too. So we do not have video from Friday. But we do have sound. And so they told me that they put sound up there. When did you last check? Oh, last night. Okay, yeah.
I just checked it a few minutes ago.
And there's no sound there?
There wasn't any post on the website.
Can someone search YouTube right now? See if you can find the sound on YouTube. They put it on two places, right? They put it on their website. They also put it on YouTube. So let's find out whether it's there on YouTube. Someone search right now if you can. I guess even I can search. I'll let you do that, though. Anyone searching right now? Yes, iPad right there. Okay, but yeah, we have that problem with that lecture, so yeah, I don't know what happened. We had two ways to record it, and both ways didn't work video-wise. But we do have sound, and sound is, I think, for this one, all you need, because during that last lecture, I pretty much was going through the module. So you have all the notes in front of you. You just have to figure out what page I'm on as you're listening to it, but that's not difficult to do, right? I wrote some stuff down, but very little actually, and those notes you have online too. You just don't get to see me writing it in real time. And from what I hear from you anyway, you don't see that anyway with this, because you hear the voice, and then 20 seconds later you see the writing or something like that, right? So we don't have the video, but we have pretty much all you need, right? Which is the sound. So sorry about that. I don't know what happened. But you got enough to go on if you were not there. And there were a lot of people who were not there. So, okay. Did you find the sound?
Still waiting.
Still waiting. Oh, okay. All right. So I guess what I'll do is just continue here. So homework 3 is due Thursday. There's a new version online, but it's not really different from the previous version. I guess in discussion you talked about this, and that in part D, the definition of Z may not have been clear enough, and now it's defined better. Well, it was defined better in the discussion section, but it's also defined better in the new version that's online. The new version is not different from what you had before, so it's not like you have to change anything if you interpreted Z correctly, which I think most people probably did. Let's see, we have a new module online. This is module 7. It's going to be what we go into next after finishing off bulk micromachining. This is on mechanics of materials. Any questions about anything? Okay. And you see we have a new email alias. You saw Brian send that around, so we created an alias for everyone in the class. You can use that same alias to email everyone in the class if you want to. So just look at Brian's email, look at the thing. I think it's ee245-class@imail.something.something.something. Okay, so we have that alias that you can all use at least. Okay, so today what we'll be doing is finishing off bulk micromachining. Last time we went through a lot of bulk micromachining. And I guess if you didn't watch the video or you haven't looked at the notes at least, you may not know what I'm talking about right here. But bulk micromachining is pretty much similar to surface micromachining, except all the micromachining is done to bulk silicon. And we went through all sorts of different types, and that I've turned very light blue here because we've already covered it in this topical outline here. But anisotropic etching, boron-doped etch stop, electrochemical etch stop, isotropic etching of silicon, deep reactive ion etching, which we covered before, but this time we covered more aspects of it, like footing, which is also an important thing that you need to understand. So all of these things, they were in last lecture, and I guess you didn't have a chance to watch last lecture. I don't think you need to know any of that for what I'm about to cover today. So you can go back and study it, after today's lecture. It's not going to affect your understanding of today's lecture. At least I don't think it will. Okay?
No, I didn't see it.
No sound on YouTube still?
Yeah, well, I couldn't see anything that points to the lecture.
Can you go to the regular website and see if the sound is there?
There's nothing posted here. So lecture 11, the last.
Okay. So on the website for this class, it's not there yet either?
Oh, for the class.
Yeah, for this class. Yeah, go to this class's no. The website where they post this class's lectures.
The one where they posted the lecture.
It's not even there? I got an email that assured me it was there by the guy from the media center who does this stuff. Anyway, he may be listening right now, so he's hearing this, so let's see if that gets up on the site. But at least there should be some sound. He's told me that they got the sound, just not the video. So there better be some sound, because I don't want to go through that again. All right, so today we'll continue with bulk micromachining and just one aspect of it, which is wafer bonding. And then we'll finish this up, and we'll start Module 7, which is mechanics of materials. And in mechanics of materials, we'll talk about basic things, stress, strain, which we'll do today, really just definitions that you have to use for mechanics. Then we'll start talking about thin films, stresses, thermal stress, residual stress, stress gradients, internal dissipation, material properties for MEMS. And we won't get through all of this today, but that's sort of where we're heading. So let's go to Module 6, back to Module 6, where we have this much more to go here. And we're going to discuss wafer bonding now. So wafer bonding is a technique to get two different materials, two different wafers together. So it's bonding at the wafer scale. So here's an example that you can see of one reason why you might want to do wafer bonding. You may want to make a mechanical structure, a micromechanical structure that's movable, but that's very thick, and it can move a long ways here. And so you see what's happening here is one wafer has been etched to create this big gaping hole here. The other wafer has been bonded to this whole thing, and then you etch away all this wafer here till you finally end up with a thickness that you like. And this thickness can, of course, be much greater than you can get in surface micromachining, because it starts out with a full wafer thickness. Depending on your wafer size, that can be anywhere from 400 microns to upwards of 600 or more microns. Okay, so you can have very thick structural materials. Usually you don't want them that thick. Usually you want them maybe 50 microns or something, 100 microns. So you can shave a lot of this down to get whatever thickness you want there. And so how is this done? Well, this is done through a process called fusion bonding. And there's many different types of bonding processes that I'll talk about. Fusion bonding is when you take two ultra-smooth wafers. So the roughness has to be very small, so less than a nanometer of roughness in order for this to really work well. And you sort of bond them without adhesives or without really even applying external forces. So if your wafers have this kind of roughness, and you clean them, give them O2 plasma, hydration, or do an HF dip, right? So you do some kind of hydration here so that you get some OH bonds on this, or you have some HF on this, and then you take the two wafers and you put them together. Okay? And so just like the capillary forces that cause stiction that we studied, if you take these two wafers and put them together, they're going to stick together. Right? Then you take those two wafers, you put them in a furnace, so you get hydrogen bonding that keeps them together. Then you stick them in a furnace and you anneal them at a high temperature, so 600 to 1200 degrees C. Okay? This brings the whole thing, this basically melds the silicon together. Okay, until you get a really strong bond between silicon and silicon. You can also do this silicon to silicon dioxide. Okay, but this is fusion bonding. This is where you actually take the whole thing to a very high temperature to get these bonded very well together. Okay, so this is one style of bonding that people have used quite a bit. Here's an example of exactly the process that we were looking at there, something similar to that. So they fusion bonded a silicon wafer that had been etched, you can see here, to another silicon wafer down here. And then, of course, they cleaved it at this point here, so you can look at the edges to see how they're bonding together. And so this is something you can make. This is sort of like a pressure sensor, sort of a pressure sensor. It seems a little thick for a pressure sensor there. But the way this works is if you have no pressure in here and you have some pressure out here, then what's going to happen is it's going to bend this down, right? And you can sense that bending through either piezo resistors on the top of this that detect the stress in this film as it bends, or you could even have an electrostatic case where you put an electrode down here and you measure the distance between these that come together. So that's fusion bonding. Okay, and it's a great way to bond. So arguably with fusion bonding, you can get one of the best bonds possible if you're doing a bond type micromachining process. However, one drawback behind it is that it's a very high temperature process. And so there are some things that you don't want high temperature around. Like say you have other layers in addition to those wafers you want to bond together that can't hold up to 1,000 degrees C. Okay, so then you want another form of bonding, and another popular method of bonding is Notic bonding. So what this is it uses an electric field to assist in bonding. And so it bonds an electron-conducting material to an ion-conducting material. So an electron-conducting material, obviously silicon is one of them. But an ion-conducting material is something like sodium glass, which is the same as Pyrex. Right? So that's glass that's impregnated with a lot of sodium ions in it. And so the mechanism for doing this is sort of shown to the right here. What you do is you take the silicon and the glass and you press them together. You still need to get this up to temperature, but it doesn't have to be a very high temperature. It could be temperatures between 180 and 500 degrees C. You then apply a positive voltage to the silicon. And it can be a very high voltage, from 200 volts to 1,500 volts. The positive voltage repels the sodium ions in the glass. So at this high temperature, those ions become more mobile. Right? So that's why you got to get the temperature up a bit so the ions can be mobile. And that electric field then pushes those ions away. You get a net negative charge at the glass surface then. And that negative charge together with the positive charge on the silicon really compresses all of this together so that you can get strong attractive forces and an extremely strong bond between the glass and the silicon. Okay, so this is a Notic bonding, another very useful method for bonding. And so you know when bonding is complete, because when you pull these together, when those sodium atoms goes away, of course you're changing the charge across the capacitor. You can watch that current go through this. And when that current is completely gone or stabilized, you know that everything's complete and you can stop. Okay, you know that you have a good bond at that point. And so the advantage of Notic bonding is that very strong pressures with electrostatic attraction. It smooths out defects. Okay, so one of the big problems, I guess, with fusion bonding is this thing right here. You need ultra-smooth surfaces, right? Less than a nanometer of roughness. Okay, ultra-smooth surfaces also means that it needs to be extremely clean, because if you have a particle on the surface, right? If I had one particle, if I was trying to bond two wafers together, say there's my wafer here, and two wafers bonded together. If I have just one particle right here, how much damage do you think that's going to do to this bonding? Quite a bit of damage, right? What's going to happen is you're going to have a ring or circle around that particle that's going to be not bonded. Okay, and maybe very small portions are actually bonded away from that particle. Okay, so that's the problem with wafer bonding, and that's why a lot of people have preferred surface micromachining as opposed to bulk micromachining where wafer bonding is needed. In wafer bonding, you really need to have a clean room that you're doing this in. Because if you get any contamination like this, it could kill your yield quite a bit. Okay? And so fusion or Notic bonding actually helps out a little bit with this. Because in Notic bonding, the electric fields are applying a huge amount of pressure between these two wafers. And so, for example, with this wafer here, this is what happens. So the wafers are sort of together right now, but they're not anotically bonded. And so this is what happens after time with anotic bonding. Okay, so this is after 5 seconds. You can see the wafers sort of coming together here, but there's still a large portion that's really not bonded yet. And then out here, you can sort of see how everything keeps going. After 8 minutes, the bond is 98% completed. So what's happening is, right, those electric fields are just pushing these things together. Now, if I had some defect here, say I have some particle right there, then in a fusion bond, that would be death. Right? In a fusion bond, that particle sitting there would keep these wafers apart just enough that you're not going to get a lot of bonding around this. So this is what happens with fusion bonding. But in anotic bonding, what would happen is if I have this wafer here and I have that particle here, well, I've got a lot of attractive force between those two wafers. So that attractive force is going to be strong enough that it's actually going to take the wafer above and bend it around that particle such that you will get bonding everywhere except in a very small vicinity around that particle. So in other words, you may lose only one device, one die there, as opposed to losing a lot of die in the fusion bonding case. Okay, so anotic bonding is a very popular way to bond, in part because you can get higher yield off of this, even if you don't have the cleanest clean room in the world. Okay, so those are two types of bonding. Then there's a bunch of bonds that you can do between metal and silicon. And so one of these is, say, eutectic bonding. Okay, so in eutectic bonding, what you would do is as shown here. It uses the eutectic point in a metal silicon phase diagram to form silicide. So this is a silicidation reaction. Silicon and metals, if you take them up to a high enough temperature, will react with each other. If you're familiar with CMOS, integrated circuit processes, you're familiar with silicidation to a good extent. They use this to lower the resistance of polysilicon lines and sources and drains. Gold and silicon have a eutectic point at 363 degrees C. So the temperatures are very reasonable, quite low here. It's a low temperature process, and you can bond slightly rough surfaces. For CMOS, if you're using integrated circuits, there's an issue with gold contamination if you're trying to do this with gold. And usually gold and silicon is the type of eutectic bonding people try to do in these sorts of things. I'll also warn you that this also suffers from uniformity issues. And that is, if you try to use this kind of bonding, usually what they're doing is device-to-device type bonding. So you'd actually have a wafer, and you'll have, say, some gold pads right here. You may come in with a silicon wafer that has been patterned like this. So all that could be silicon. And then you'll let this bond here. Okay, by taking it up in temperature, getting that silicidation reaction, that'll bond all of this together. Part of the issue there is some may not react. Okay, so some may go ahead and form the eutectic layer. Like maybe this one here forms a eutectic. Maybe that one forms a eutectic. But maybe you'll have no reaction here. Okay, so it's not as consistent as you would like it to be, and so that's what holds people back on these types of eutectic bonding. Why is it not perfect? It's not perfect because maybe these aren't perfectly in contact. Right? Maybe you're not putting enough pressure between these here. So that's just one warning I'll tell you about eutectic bonding. It's a great way to do it, but is your yield going to be very high? That's a question. Okay, solder bonding is another way to do this. So this is basically taking two solders. And the picture would look very similar to what I've just drawn up here. So I would have something like this, where now on these two wafers, I may have solder. I may put a block of solder right here. Maybe that's a gold tin or something like that. And then when I take this up in temperature, it behaves just exactly the way you expect solders to behave, right? This is going to sort of flow into that. And that can create a nice, strong bond right here. The issue with solder processes to try to get MEMS together, like bump bonds and that sort of thing, is that you can get outgassing. And so what happens is not only do you get this solder forming, but right, gases come out of this thing. And if you're trying to do solder bonding for encapsulation, of course those gases are no good. They can also splatter on devices around you. So solder, people have tried it as well. It's not an ideal solution either. Another way to get bonding through metals is thermal compression. And this is commonly done with electroplated gold. And so in this case, what's happening, it looks exactly the same as all this other stuff, except now you're not taking anything up in, well, you could take it up in temperature, but you don't have to, right? But now you're using pressure to just physically force these two metals together. Okay, and it turns out that you could actually get a very good bond this way. Just physically pushing them together. This is the way a lot of devices are vacuum encapsulated on the macro scale. People have tried using this on the micro scale too. And so this is an example here where thermocompression bonding has been used to bond a fabricated structure. This is fabricated using a process called the hexyl process, which I'll talk about in a second. But it's a very thick structure here. It was created out of a mold and then flipped over, and you can see the gold down here, right? Then it was thermocompression bonding onto this gold piece right here. Okay, so this is actually a device and process that worked. The only problem with this is they wanted to use this as a gyroscope. Okay, so it resonates, so it vibrates. It has to have very high quality factor, and it turns out quality factor has a lot to do with how good your anchors are. And so in this case, was this bond good enough to create a good enough anchor? Well, this was never pursued enough to really answer that question here. But this is one way to get micromechanics together with whatever else you have on this wafer here. Just do a compression bonding here. It seems seemingly a simple way to do it, but more work has to be done to understand that. So as far as this structure that you're seeing right here, this structure was made using a process that sort of combines bulk micromachining with surface micromachining. And I guess that's what I'm going to talk about now. I should have, really before this, I should have had one of those slides that say combinations of bulk and surface micromachining. So what this is work by John Heck, actually. And so you can see what's happening is you first take some silicon here. And the idea of this is to get very high aspect ratio structures. You see these structures? These are very high aspect ratio. I guess I don't remember how thick these things are, but they're pretty thick, 20 microns or something like that. I'm sure you can make them even higher than that. But the thing is, with the surface micromachining, it's tough to do something like that. In bulk micromachining, you can do that, but it kind of gets expensive to make these very deep etches. So that's the one thing about these deep reactive ion etches that people don't say a lot about, that if you're doing a lot of deep reactive ion etching, it could get expensive because you're using a lot of gases, a lot of process gases, to etch through some very deep trenches in your silicon here. And so in this case, that's what you're seeing happening here. You're using a deep reactive ion etch to etch these deep trenches that are actually creating a mold now. So this now serves as a mold for the actual structure that you want to make. And so what they do after this, they deposit a sacrificial oxide, they deposit an undoped polysilicon, then an in situ doped polysilicon here. And then I guess to make it more conductive, they can put a nickel in here using an electroplating process. And this is an interesting electroplating process because it's electroless nickel. You don't need an electrode to do this. And so I guess I'm telling you now it's possible to do something like that, to actually plate nickel this way. But then what they do is they dip this into hydrofluoric acid to remove all of this oxide here. And when you removed all this oxide, now you can take this out of this. So you effectively used this original silicon piece as just a mold. You did reactive ion etching once to create a mold. Then you deposit all sorts of things on it. And you could take out this piece. And this piece can look pretty complicated. It could be something like this, right, which is sort of this hexyl type, a honeycomb type structure here. And so when you create a structure like this that has, a lot of complexity, this can remind you, say, of our bridges, right? So you look at the Golden Gate Bridge and all these other bridges, right? If you design your beams correctly, your I-beams and that sort, you can make it very strong. Okay, so this is actually a very strong structure right here. It has very thin supports, which is nice for a gyroscope because you want these supports to be as compliant as possible in a gyroscope. In one direction, which is this direction. They're very the rotating direction here. The vertical direction is very stiff, you can see. So it's a nice process to make something like this, and it was done using that hexyl process and then doing a bonding using a thermocompression bonding. Some other processes that can create MEM structures that kind of combine surface micromachining and bulk micromachining. So one of these is SOI MEMS. So in SOI MEMS, you're not just using the silicon substrate as your MEM structure. You're actually using the device layer in a silicon on insulator type wafers. You buy an SOI wafer, which is silicon, insulator, and then a handle wafer, silicon down here. You can buy SOI wafers with very thick silicon on top of it. Device people will usually use very thin silicon. MEMS people will use the very thick silicon. And so in this process, what they would do is do a trench etch right here using deep reactive ion etching, fill that with a nitride. And what that nitride does is it takes this conductive silicon and it puts an open between this and this. Okay? And so then you can come in, you can build your circuits right here if you wanted to. And you can have passivation and interconnects come in there. And then what you do finally is you etch this to create your structure. I guess this is side view and this is a top view here. And then you etch out the oxide underneath this. So it's like a combination of surface micromachining and bulk micromachining, except your structures are on a nice thick bulk device. Okay, so this is kind of a nice process. This was developed a while ago by a guy named Tim Brosnahan, who then went to Analog Devices. And Analog Devices was thinking of making products in this, gyroscope products in this. And maybe some of their products do have this. And so in the end, here are some of the things that you can make with this process. So this is actually a mirror here that Analog Devices was trying to make back in the day when optical communications for MEMS was something that was interesting. That has gone away, but maybe it comes back, who knows. But this is one process, this process you just looked at, that achieves this. Integrated together, you could see with circuits, right, which is something Analog Devices is famous for, getting MEMS together with circuits. Okay? Finally, I guess I'm just going to reference this just because it's a reference. This is a very old process that Noel McDonald at Cornell had developed. This was before people had deep reactive ion etching. But it's just an illustration of how smart you can be if you don't quite have the tools to do deep etching and that sort. So in this case, the screen process, put photoresist on, maybe a hard mask like an oxide, etch this. And so you can do a deep silicon etch here. This was not quite as deep as a DRIE etch. You can then cover this up with a PECVD oxide, etch straight down to remove the oxide at the bottom here. Then you've opened this stuff here, in which case you can then do a silicon etch. And if you do silicon etch long enough, these will come together, and you'll free this portion right here. And so in this way, you can get very thick MEM structures here using what's called the screen process. And I don't think this is really used anymore. I'm just telling it to you because someone may mention scream to you, and I just want you to know what it is. Okay? But that's it for bulk micromachining and derivatives of bulk micromachining. So with that, I'm going to finish talking about processing for now. Later on, after we've talked about circuits and sensing circuits for MEMS, I will go back into talking about integrating MEMS together with transistor circuits. Okay, that's when you'll understand more about what's important to do with that type of integration. But for now, let's move on to our next topic, which is mechanics of materials. And for that, I'm going to go through, initially at least, the online notes for this. Initially, I'm going to do this because most of the initial stuff is definitions. Okay, I just want to define a few quantities for you, and then we'll start using those quantities over and over again. Okay, so mechanics of material, we went through this outline at the beginning of this lecture. Chapter 8 in Centuria will say a good amount about this. And so this is sort of, we're going back into the I guess, analytical stuff, technical analytical stuff. We've been playing around with processing all this time, not that much analytics. But we're about to slow it down and go into some deep derivations of certain things again. And for those who are not mechanical engineers, this is where you will struggle a bit. So the EEs may not like, well, not like this material, but may be less, on a less stronger foundation going into this material here. So why do we want to talk about this? We want to talk about this because we want to understand what's happening here. Okay, we want to be able to model that and prevent it in the future. So let's go ahead and start. So let's talk about elasticity. And to talk about elasticity, there's a number of different definitions that I want to make. And these are things that are going to become second nature to you, or at least they should become second nature to you. If you're an EE, what's second nature to you? Well, resistors, inductors, capacitors are second nature. At least they should be. Right? These types of concepts, voltage, current, right, it should be second nature. These concepts here, stress, strain, Poisson ratio, Young's modulus, these should become second nature to you in order to handle mechanics well. Okay, so let's talk first about an important one, that's normal stress. Okay, so this is illustrating what normal stress is. So if I take a block like this and I apply forces on both ends, okay, I'm applying to this a tensile force. Right? In this case, I'm applying this force normal to the surface here, which has a surface area A. Okay, if I apply this force normal to that surface area A, then I'm applying a stress to this whole thing, and I can call that a normal stress. Okay? Now, stress is defined as a force per unit area, so it's like a pressure. All right, and so stress is given the symbol sigma, usually, and is equal to force, this force that I'm applying at this end, divided by that area. Okay, so it's a force per unit area, and the standard MKS units for this is newtons per meter squared, which is what the definition of a Pascal is. Okay, and so in this case, for this argument, I'm assuming that the force is uniform over this whole area. Okay, but the total force being applied over that whole area is F when I sum it all together. Okay? Now, this is sort of a macroscopic definition. In my macroscopic definition, I have to enforce this. I have to say that force is uniform over that area, but in general, it won't be. Right? Because what we're usually going to be working with is a microscopic type situation. And so what do I mean by that? What I mean by that is usually we're looking at some tiny little element within this whole thing. Okay, so that this is a differential element of material. Within that whole block there, and that differential element I could sort of equate to this down here. Okay, so the microscopic definition of stress is a force per unit area acting on the surface of a differential volume element of solid body. Okay, so my force is going to be acting here, but I'm assuming that this edge is infinitesimally small. Right? So I have only one force there. And the stress then is going to be that one force divided by whatever the area of this wall is here. Okay? So this is why we make this definition, right? A force per unit area, a stress. We talk about stress because usually we're talking about stress as applied to a tiny differential element. Okay? And so you know this is a precursor to what we're going to do later on. We're going to take actual beams, we're going to start bending them, and then we're going to start integrating over these little elements on this beam to get the total effect of each of these little elements and the stresses applied to them on the total beam. And that's the way we're going to figure out how much this beam is going to bend under a certain amount of applied stress or intrinsic stress within this beam. Okay? Yeah, so here in this differential thing, we're assuming the stress acts uniformly across the entire surface of the element, not just as a point. And we can do that because it's differential. It has no surface, but it has an infinitesimally small surface. Okay? All right, so that's stress. So what happens when you apply a stress? When you apply a stress, of course, materials react to this stress. And you know how they react, right? If you stretch a rubber band, it gets longer, right? Well, everything gets longer as you apply a stress to it. So if I'm applying these forces to the edges here, what's going to happen to this block, it's going to get a little longer. Okay, if initially it was at L, and after the stress is applied, it's now L prime long. Okay? And so we define the strain as the fractional change in length. Okay, so we give it a symbol epsilon, okay, which sort of makes it confusing at some point with EE's permittivity, right? So you have to juggle these different constants or variables that we're using here. But that's simply just L prime minus L divided by L, right? It's a fractional change there. So delta L over L. And so because the units of L, delta L is meters, the units of L is meters, it's unitless. Okay, so there is no unit for strain. You can just give strain as, say, 1 ppm or something like that, 1 part in 10 to the 6. ppm is part per million. Right? Or some people feel they like to use a unit actually for this, even though it has no units. Right? People like a unit, and usually they like this because strain is usually very small. It's on the order of 10 to the minus 6 or something like that. Right? So it's kind of bothersome to say, okay, I have 1 times 10 to the minus 6 strain or something like that. So people like to use a unit called a microstrain. Okay, so it's given this kind of symbol, and it's called a microstrain. If someone talks about microstrains, you know what they're talking about. They're talking about a unitless quantity that just really equals 10 to the minus 6. Okay, 1 part in 10 to the minus 6, which is the same as, what's it, 1 part in 10 to the 6, which is the same as 10 to the minus 6. Okay? And so you know, I just described strain as what happens after you apply this force, right? I'm applying this force to the edges of this thing. This thing reacted by getting longer. And of course, there's going to be some function between how much reaction you have here to what force you've given it. And for that, I can plot stress versus strain here. And if I do that, I would get a curve like this. All right? Why they plot stress on the y-axis, strain on the x-axis, I don't know. I would have put stress down here, strain on the y-axis, but this is the way it is. Okay, so this is sort of the convention here. I'm saying it's convention because at small stresses, at low temperatures, okay, strain is found to be proportional to stress. Okay, so that's kind of a nice thing. This is a linear function between the two of them. So that means if I put a stress on this, this is going to pretty much look linear until you get to a certain point here where things start to not be linear anymore. That's where you're starting to lose, you're trying to leave the elastic regime. Okay, but in a lot of our applications, we're going to stay in the elastic regime, especially for MEMS, where we have very long beams that move a very small percentage of their lengths. That's a pretty linear situation. And so we'll be able to use this regime quite a bit in this. So this is sort of like linear regime. But in that linear regime, we can define a slope equal to what we call the Young's modulus of elasticity. Okay, you've seen Young's modulus before in some frequency equations that I threw at you a little earlier. Now you know exactly what Young's modulus is. It is just that proportionality constant between stress and strain. Okay? And because strain is unitless, right? Strain is equal to stress divided by Young's modulus. Because strain is unitless, the units of Young's modulus are the same as stress. Okay? So it has to be in pascals or gigapascals. Okay? And usually Young's moduli, I mean, I think I've given you numbers before. Polysilicon, 150 gigapascals. So there are lots of pascals. Gigapascals is usually what you're looking at for a lot of the materials that we're working with. Okay, so that's strain. So in addition to stress and strain, you should also understand another quantity, and that is the Poisson ratio. Okay, so what is the Poisson ratio? Same situation. We're applying a stress, which is really a force that we're applying over the cross-sectional area of this beam. And this time I'm being very specific about where I'm applying this force. I'm applying it in the x direction, because what it does is it does create a length change in the x direction. But you're probably familiar with the fact that if you take something and you stretch it this way, you're not only making it longer, it usually will get thinner, right? And so in addition to the length change, you also get a change in the width. So again, we're calling W the original width, W prime the new width after applying this force, but this force is now being applied in the orthogonal direction to the width change. Okay? And so this is uniaxial strain, but you get contraction in directions transverse or orthogonal to the uniaxial strain. And so this is a negative strain. Okay? If something contracts, that's a negative strain. If something is being stretched, that's a positive strain. Okay? And so this strain is going to be defined as W prime, the width after the stress, minus W, the width before the stress, and it's a fractional width change. And so that's going to be equal to a minus nu times epsilon x. Okay, so this is going to take on a negative sign here. But nu is the Poisson ratio. Okay, and because everything in this, the e sub y, or sorry, epsilon sub y, epsilon sub x, they're unitless, so must the Poisson ratio be unitless. And here are some examples of Poisson ratios. So inorganic solids, so things like polysilicon and that sort, we're looking at something on the order of 0.2 to 0.3. Elastomers like rubber, right, that's 0.5. And so that sort of gives you an idea, right, of what kinds of quantities we're talking about for the Poisson ratio. Okay, and it turns out that people use the Poisson ratio quite a bit in a lot of MEMS. So they may be applying a force in one direction along this axis when they really want a change in length or some movement to occur in the opposite axis. So this is one way to be able to apply a force one way and get a reaction the other way. Could be very useful. Shear stress is another thing that you need to understand. And so also, all of these things that I'm giving you are just pure definitions here. Okay? So in shear stress, what you're doing is you're taking a block of material, like before, except now, instead of applying the forces uniformly across the cross-sectional areas along one axis, you're now applying a force along the surfaces, the opposite surfaces of this. So I'm applying this force to this surface area over the top there. Okay, so that A corresponds to the area of this top surface. And I'm now applying this force sort of tangent to that surface. Okay? And I'm applying an equal and opposite force, just like I did with the stress case. Equal and opposite force here on the bottom face of this thing here. And so what that's creating is a shear force. It's creating a force that's sort of pulling these things apart. Okay? And in doing this kind of analysis here, you always assume, you pretty much assume that you have compensating forces as well. So if I'm applying these shear forces here, then I'm not going to allow this block to rotate, okay, because I want it to shear. So to prevent it from rotating, we assume that we have equal and opposite forces that are see, this force would make this rotate in that direction, but this force will cancel out that rotation. Okay, so you assume that you have an equal and opposite force that cancels out all of that rotation there. Why do we do that? We do that because usually what we're considering is, again, an infinitesimal block within a gigantic block, right? So I have a gigantic block here, and this block, I guess I drew that wrong. Let's fix that. So this is an infinitesimally small block within that gigantic block, right? And so those infinitesimally small pieces, right, they can't rotate there. If they see that shear stress, they're going to shear and not rotate there, okay? And so we assume those compensating forces by convention. And shear stress in the end is, you know, like before, force per unit area divided by, or force per unit area parallel to the surfaces. Okay, so it's force divided by that area, but now it's this force and that area. Okay, where the force is sort of being applied in tangent to that surface. Okay, again, it's pascals. This is going to generate a shear strain. And by the same token, we're going to take shear strain as being equal to this shear stress tau divided by a shear modulus. And the shear modulus turns out to be the same as the Young's modulus divided by 2 times 1 plus the Poisson ratio. Okay, you could derive that yourself. I think that's derived in the book as well. Okay, but those are the basic concepts you need to understand in order to work a bunch of these mechanics of material problems that we're about to do. Okay, so it's shear stress and strain. It's the Poisson ratio. It's just strain, and it's normal stress. Okay, so these are all definitions here. I've sort of gone through them fairly quickly because they're just definitions. Okay, but there's also 2 and 3D considerations for all of these. So we've been talking about all of this sort of in the x direction mainly for a lot of these things. Well, you got these strains in all directions. Okay, so if I take a differential volume element like this, I'm going to have stresses, potential stresses along all the faces of this thing. Okay, so I'm going to have it in all 3 directions. And for each of these stresses, right, I'm assuming that I have, like for this sigma sub x, I'm assuming that I have an equal and opposite sigma sub x on the other side. Okay, why am I assuming that? Because I'm assuming this block isn't going anywhere. It's a differential element within a giant or a larger block, right? So this thing's not going to go anywhere if that larger block is not going anywhere. Okay, same thing for any of these stresses here. So you see this Tz of y? Sorry, so shear stresses. Same thing for shear stresses. So this tau sub zy, which is a shear stress, right? If that were the only stress acting that way, this is going to make this thing rotate in that direction. But you notice there's a tau yz here to fix that and cancel that out. Okay, so for every shear stress, you have to have an equal and opposite shear stress, and I guess that's sort of illustrated by these equations down here. Okay, so everyone get that concept? This is a small block within a large thing. Okay. Okay, so we can go beyond this. So that's 3D. We could take one of those out and just do 2D. So in 2D strain, right, in general, we're talking about motions of things. So either we're looking at static problems or we're looking at motions of things. But under some kind of stress, the thing contorts. Right? It can contort, but it could also do a number of different things. So in the 2D situation, general motion consists of rigid body displacement. Okay, so that's when this body, which is this square block in black, is just displacing, okay, around its center of mass. Rigid body rotation, that's where this square block can just rotate, as I'm showing with my hands right here. Okay, there's no contortions in this thing while it does a displacement and while it does a rotation. Okay, but then finally there's this deformation here, which is what I mean by contortion. So you can also have this deformation. And we're interested in this deformation here. Right? That's where we're talking about all these definitions of terms for mechanics of materials. And so when we have a 2D situation, we have to work with displacement vectors. Okay? And so what do I mean by that? So that's why in the textbook or in all sorts of texts that you're going to read about mechanics of materials, vibrations, when you take other classes in mechanical engineering, we've defined axes, x, y, and z, but we're usually working in terms of displacement variables that represent displacement vectors. So instead of saying this is delta x moving in that direction there, I'm calling this a displacement u sub x of x. Okay, I don't even have to do the u sub x. Usually they won't even put the x there. They'll just say u is a displacement in variable for the x direction, v is a displacement variable for the y direction, so on and so forth, if there's more directions there. Okay, so you'll see that quite often in these books. W is for z. Okay, but anyway, that's what these are. So that's the displacement occurring at this point here after I've applied a stress. So if I apply a stress in just the x direction here, then this is the displacement at this location. This is the displacement at location x plus delta x, okay, on this rigid body. And so in this case, we need a differential definition of axial strain. And so the differential definition we can apply for this just along the x-axis here is just going to be whatever the displacement is. It's the same as a definition of regular strain, except now we're taking into account the fact that you have two different positions right here, u sub x at this location x plus delta x, and u sub x at location x. Whatever that change in the x variable is across here, that's going to give you the change in the length across this, and divide that by the actual length of this box. So that delta x is sort of the beginning length of this box there. And that, of course, when you go infinitesimally small, is the partial derivative of ux with respect to x. Okay? So going to 2D, you have to start doing this type of thing here. We're not really going to play that much with 2D. I'm just showing you these things. But in the end, most of our problems we'll be able to do in 1D. Shear strains also. So in addition, so I'm talking about just a normal stress here, a normal strain. You could also have shear stress, shear strain, which is what you're showing right here. This is not only, well, this is contorting in many different directions. Okay, so for shear strain, really you're talking about angles now, right? When you do a shear, you're really creating that angle there. And so the easiest way to solve a problem like this is just to re-rotate this down here, have theta 1 plus theta 2 up here. So you can see that the total shear strain that you got on this thing here comes from these two angles that you formed right here. And so if we use a symmetric definition of shear strain, I can say that gamma xy is equal to just the sum of those two angles. For small amplitude deformations, which is generally what we'll be working for, then I can say that's just delta ux over delta y plus delta uy over delta x, and then the differential form of these two. Okay? Again, 2D type stuff. And so now let's go in and actually use this stuff on an actual problem. So let me slow down here. Now that we've done all our definitions and taken a look at things that you can just read over and that I didn't want to write, let's go into the other mode here and slow down and just do an example problem here to bring some of this home for you. Can someone check to see if the sound is online now? I'm just curious to see if he's listening to us. Because if it's online now, maybe he was listening. All right, so what we want to do is just take a look at an example problem here, just exercising all these terms. So what we want to do is look at volume change when we apply a uniaxial stress to a perfect box, I suppose. Volume change delta V or uniaxial stress along the x direction. Okay, so let's take an example, well, at least to look at a figure that we can use to do this. Let's take this. So this is showing that we have different stresses. It's possible to have different stresses around all these different directions to this 3D block. I'm only going to apply one, so the one that I'm going to apply here is going to be the stress in the x direction. And of course, if I'm applying a stress in the x direction, that implies that I'm doing an equal opposite one also in the x direction, but going the opposite direction, right? Because this thing has to stay in place. I have to have force balance along that. So if I apply this x-directed uniaxial strain, how does that change the total volume of this block? That's sort of the question that I'm asking here.
So upon application of sigma sub x, what is delta V? It's not there?
No, unless I'm looking in the wrong place. It shows lecture 10.
Yeah, I got a specific email saying it's there. And I think the email pointed to some website, so maybe I'll check that website after lecture.
Different place for audio.
For audio?
Yeah, I mean, it shows videos.
In the past, when we've had video problems, and we've had problems in the past too, the audio shows up in the same place. So, I mean, logically it should, because, right, if all you have is audio, you might as well let that be available too. And so, yeah, anyway, okay. Sometime after this lecture, it'll come online, because I'm going to have to make sure of that there. All right, so upon application of this sigma sub x, what happens? So I'm going to get a delta x, right? So initially, this length is delta x, okay? But this will, and unfortunately it's labeled delta x, but we'll just work with that, okay? But this is going to go after application of this stress to what? It's going to go to delta x times 1 plus epsilon sub x, 1 plus the strain sub x. Okay, that's how much longer it's going to be after application of that stress, okay? How about delta y? What is this thing doing? I know what it's doing. Let's let it stay there. Okay, so after application of delta y, what's the new length in the y direction, which is now this direction right here? It's going to be delta y times something, but times what? One minus the Poisson ratio times that same strain sub x. Okay, so there's only one strain that we're going to have to reference here, and that's the x-directed strain. Okay, and similar sorts of thing for z direction. So that's going to be the original delta z times 1 minus the Poisson ratio times epsilon sub x. Okay, and I guess in all of this thing, we're making the assumption that this is an isotropic material. Okay, and so, in other words, we're assuming that it's the same nu along y and z. Otherwise, I'd have to put a subscript under each of the nu's that I just wrote there. Okay, and so what we're interested in is the resulting change in volume. So the resulting change in volume, which we're going to call delta V, right? I can just write out what this delta V is. It's going to be it's going to be the volume based on all of these. So it's going to be delta X times delta Y times delta Z times all these factors that I multiplied them by. So 1 minus epsilon X times, 1 plus epsilon X times 1 minus nu times epsilon X squared, since I have two of those. Right? But then I have to subtract from this the original volume of this thing, which was delta X, delta Y, delta Z. Okay? So this here represents the volume after application of stress sigma sub x. Okay, so all of this is going to be equal to delta x times delta y times delta z times just a little bit of rearrangement here, 1 plus epsilon sub x times 1 minus nu times epsilon sub x, all that squared, and all that minus 1. And now what we're going to do is we're going to make a simplifying assumption. We're going to assume small strains, which is usually going to be the case. So if we assume small strains, that means we can use this type of thing, the binomial theorem, where 1 plus m times x to the n power, we could say is about equal to 1 plus n times m times x. Okay? And if we apply that binomial theorem to what we have up top, so first of all, we can write our delta v as, again, delta x times delta y times delta z, but this times 1 okay, so what I'm going to do is apply that theorem to right here. So 1 plus epsilon x times 1 minus 2 times nu times epsilon x minus 1. Okay, and that then comes down to delta v is equal to delta x times delta y times delta z times 1 minus 2 times the Poisson ratio nu times epsilon x. So in the end, this is an expression for my volume change after seeing just a stress change in the x direction. Okay? And so what can I say for this? So now we can get sort of an understanding of what these Poisson ratios mean. So if I had a Poisson ratio equal to 0.5, which remember was the Poisson ratio for rubber, right? Then what does this say about the volume change? That means there's no volume change, right? Which is what you know about rubber, right? Rubber is purely elastic, and so if I stretch in this direction, it's going to shrink in that direction to the point where there's no change in volume for the whole thing. Okay, if I have a Poisson ratio less than 0.5, which is what I have for most MEMS materials, right, then there is a finite change in volume here. Okay? So just from very simple analysis like this, we could sort of get some sense of what these constants tell us, right, for different materials, rubber and that. If I have a Poisson ratio of 0.5, it's rubber, and it's going to react the same way as rubber. I could stretch it, volume won't change. Okay? And so we could continue doing things for this, right? And for isotropic materials in general, let me see if this is easier to do without writing. Yeah, it is. So if I have isotropic materials here, I don't want to write all this stuff, so I'm just going to do it like this. That means things are the material properties are the same in all directions, right? So I have only one nu, I have only one Young's modulus for this material. The complete stress-strain relations for this isotropic material just go into sort of a generalized Hooke's law here. So epsilon sub x, the strain in the x direction, becomes 1 over Young's modulus times the stress applied in the x direction minus Poisson ratio times the strains applied in the other directions. And same for all these other directions here. So epsilon sub y becomes 1 over Young's modulus times sigma sub y minus the Poisson ratio times the strains or stress is applied in the other directions, and so on and so forth for all of these. Okay, and here are the equations here just for the shear stresses and shear strains. Okay, so for a pure 3D situation, this is what it looks like. And so what page? What's that? The G, oh, that's the shear modulus. So that's the thing we defined. One of these is escape. Or none of them are escape, and I have to open this in escape. All right. We'll do that. Okay, so if I go back here, remember we talked about the shear modulus right here? Okay, so we're talking about shearing, that relationship between the shear strain and the shear stress is G. It's the same as E, same as Young's modulus, but for the case of shearing. And it's related to the Young's modulus just by the Poisson ratio. Okay? All right. Let me save that. So let's go back to this mode here. So that was 13. I just wanted to show that because now what I want to talk about is an important case, which is plane stress, where I'm going to use that. So what do I mean in this plane, by plane stress? I'm going to talk about a common case that you see very often here. When you put a thin film coating on a substrate, on a rigid substrate. So let's just say that, common case. Okay, so this is something you've done many times, and in this homework you're doing, or you did in the last homework, and more of it in this homework here. So we're going to take a substrate, and we're going to put on this substrate a thin film. Okay, and so on this thing I'm going to have a couple regions that I'm going to care about. And it turns out that when you put a thin film on the substrate that's patterned like this, you can see it's patterned, it's not reaching the end, it's not covering the whole substrate, but I put this film on the substrate and then I patterned it using some kind of etch. So it has these edges here. Okay, so I'm going to define this region right here as being some kind of edge region. And let me do that in a different color. So that's my edge region here. And this is an edge region that's about maybe 3 thicknesses from the edge. Okay, that's going to be an interesting place for me because if I zoom in on this whole thing, what I'm going to see is something like this. So I'm going to see the edge. Now let me leave enough. The edge of my substrate here. So that's the substrate. And then I'm going to have some of that film right here coming up there. All right, it's going to be nice and flat in the region that I'm showing right here. But then when I get closer to that edge, it's going to do this. It's actually going to come up and be thicker in that region and sort of look like it's pointing up. Okay, so this is that region here within 3 thicknesses that I'm calling my edge region. And so let's say a couple things about this region right here. So what's happening in this region? Well, one thing we can say about this region right here is that the stresses in this region near the center of my device, this is where the stress in the z direction is going to be 0. right? I'm not going to have an awful lot of stress in that region up here. So this is kind of a stress-free region in the z direction here, but not necessarily in the x and y direction. Okay, so in the x and y direction, I'm going to have some stresses. And those stresses then are going to cause some kind of force right here. Right, so this is going to be some force going in this direction here. And this force is not equal to 0. Right, that's going to have some finite amount of force there. But then along this edge here, what does the force have to be along that edge? Yeah, it's got to be 0. It's not surrounded by anything that can exert that force. So this force right here has to be equal to 0. So I've got this region right here where I've got some forces on the inner parts, but I've got no forces on the edge part here. And so that's why you start seeing something like this. Right? You actually have this region here where, because you don't have a lot of force in here, you actually don't have a lot of Poisson shaping, right? Which is why this is not as thin as this part right here. Okay, but in addition to this, you have a lot of shear stresses going on here. And you can see that you have an imbalance of forces around this as well. So you eventually develop forces, especially at this point here. Now remember, we talked about the fact that points are places of very high stress, right? We call that a sharp point. Okay, that's a point of very high stress. What you're going to do is you're going to develop a peeling force at the edge of this film. Okay, and that peeling force is happening because you're at the edge. You don't have any forces going in this direction. You do have lots of forces going in that direction. You're going to create a shearing force that's actually trying to pull that thing up and out. Okay, and so when you have too much stress over the top of your substrate, this is why films peel. Okay, and this can happen. You know, it does happen definitely if you etch this film and actually create a pattern film like this, so you can actually have an edge. But it can even happen if you have so much stress in your film to films that are not patterned, like nitride films that are deposited too thick over a substrate. First of all, the stress could be very large within the center of that film. You can then get a crack in that film. Now that crack creates this edge condition, and now everything comes up. Okay, so this is one way you can have films that curl up even before you release these structures. They're just delaminating from the substrate. Okay, so this peeling force here delaminate the film from the substrate. Okay, that's an effect we'll talk about later on in more detail. Yes.
Is it thicker on the edge due to stress, or is it thicker just?
It's thicker because of the Poisson thing. So in this case, right, you have lots of force on both sides there, right? And so when you apply that stress, right, you're stretching it and you're making it thinner. But in this edge here, you don't have as much stress there being applied to that, so it's actually thicker. You don't have the Poisson ratio pulling that down. So it actually becomes thicker there. But if you do the real analysis for all the forces, you'll find there's a force, there's a peeling force that comes out of that. But we won't do that now. What I want to do now is just handle the easy case here and sort of look at just this region out here. Let's just take a look at this region. Okay, so in this region, we're going to get two components of stress, right? We know that sigma sub z is equal to 0, right? We don't have any stress going up the top because that's an open edge again. Any open edges, you don't have stresses over the surfaces of this thing. Okay, but we do have lots of stresses in plane, so we're essentially going to get two components of stress. Okay, one of them is going to be, well, two components of stress causing two strains. Okay, one of them a strain in the x direction, which is going to be 1 over the Young's modulus, times those equations we just looked at. So there's going to be a sigma sub x minus nu times sigma sub y minus sigma sub z, which is 0 in this case, plus sigma sub z, which is 0. Okay? We're also going to have a similar equation for the strain in the y direction. So I'm going to be able to write sigma sub y minus nu times sigma sub x plus 0, which was the stress in the z direction. Okay? And so we're assuming that we have an isotropic case. So we're assuming plane stress. Let me write that down correctly. Right? No z direction. We're assuming that it's an isotropic material. So both the substrate and the film that we're putting down is isotropic, which is generally the case. That means that sigma sub x is going to be equal to sigma sub y. Okay? Same stress in all directions. And so I'm just going to call that sigma. Okay? So that basically is a statement that we have symmetry in the xy plane. Okay, well, if that's the case, and I look at these two equations right here, then right away I can also say that epsilon sub x equals epsilon sub y, which is epsilon. So the strains also I can say are equal. And now if I just take a look at one of these directions here, say the x direction, I can write out its equation. So that'll be 1 over the Young's modulus times sigma minus nu times sigma. And that ends up being sigma over, and now moving things around, E divided by 1 minus nu, which I can now write as epsilon sub x is equal to sigma, my stress, divided by, remember before there was just an E, so I'm just going to call that an E prime there. Okay, where now I have a new quantity, E prime, equal to, well, first of all, let's give it a definition, right? Let's give it a word. This is now called the biaxial. Let me do that right. The biaxial modulus, which you could see just from this equation to the left, is just the Young's modulus divided by 1 minus the Poisson ratio. So where you have situations where you have plane stress, where the stress it's isotropic and the stress is the same in all directions on the plane, it's really the biaxial modulus you have to use to determine what your strains, what your stresses will be, which will then be used to determine several different things, like how high off the plane something will bend and that sort. Now, whether you use the biaxial modulus or not is something that's going to be a point of contention later on in the course. Not a point of contention, but a point that you're going to have to figure out. Okay, you'll have to recognize when it should be the Young's modulus, when it should be the biaxial modulus, but we'll talk about that, okay, when we get to it. All right, so a couple interesting problems just exercising some of these definitions that we have. And the next one that I want to talk about is actually linear thermal expansion. So let's talk about that. Let's sort of introduce that right now. This is also going to use these concepts that we have introduced today. So first of all, let me define linear thermal expansion. So we know a couple things. We know that if we increase the temperature in a system that we have, in general what happens is that solids, they'll expand in volume, and basically they'll expand in all directions. Okay, so let me define here. Yeah, this is going to be very quick, though. Yeah, I know it's 3:30, so. So the definition here of the linear thermal expansion coefficient . So linear thermal expansion coefficient is defined as, first of all, it's given a variable alpha. So alpha sub t. This is equal to the derivative of the strain with respect to temperature. And I wrote it for the x direction here. Okay, so strain has no units. This is going to have units of Kelvin to the minus 1. And so this is going to be something that we're about to use to analyze a real problem where we're going to deposit a film at a high temperature, and then, like all situations, we're going to cool it down to room temperature, and we're going to figure out how much stress, how much strain is left in that film, and that then is going to tell us whether that film is going to peel off or whether after we process that it's going to buckle or something like that. But that's where we'll end here, and we'll continue this on Thursday. As a reminder, your homework is due on Thursday, homework number 3.